Jupiter, Saturn. These titanic worlds defy imagination. How can planets be composed almost entirely of gas? What lies behind their tumultuous atmospheres tens of thousands of kilometers thick? Like cosmic laboratories, these gas giants defy our understanding. Their atmospheres are home to phenomena of unprecedented violence. Titanic storms, monumental lighting, polar auroras of pharaonic proportions, worlds where winds blow at speeds exceeding 1,000 kilometers per hour or 600 miles per hour, planets so vast that thousands of Earths could fit inside them. Today we're off to explore the farthest reaches of the solar system to discover the gas giants. But before you set off on your next adventure, make sure you like the video and subscribe to the channel so you don't miss a thing. Thank you and have a great trip! While we're on our way to the gas giants, I'll give you a quick reminder about the planets in our solar system. But you can also take the opportunity to observe the celestial landscape through the porthole. Our solar system is made up of 8 planets orbiting the Sun. Pluto was long considered a 9th planet, but since 2006 it has been reclassified as a dwarf planet. Half of the solar system's 8 planets are rocky. These are the 4 planets closest to the Sun. You'll have understood that the 4 planets furthest from the Sun are the gaseous planets we're going to talk about. Mercury, Venus, Earth, and Mars are planets made mainly of rock and metals, known as telluric planets. Jupiter, Saturn, Uranus, and Neptune are mostly gas. They are separated from the other planets by what is known as the ice line. This imaginary line marks the boundary between telluric and gaseous planets. It lies around 700 million kilometers, or 435 million miles from the Sun, just before the orbit of Jupiter. Beyond this limit, water exists only in the form of ice. This is what enabled the formation of giant planets. Beyond the ice line, solid matter is more abundant, thanks to the contribution of methane ice, ammonia, dry ice, and water ice. More matter means bigger planets. But are they made of ice or gas? Jupiter is thought to contain a solid core at its center, larger than Earth's, made up of ice particles and dust. As its surface is very cold, it has retained its gaseous atmosphere. Astronomers divide the giant planets into 2 categories. The first includes the gas giants Jupiter and Saturn. They are also known as the Jovian planets in reference to Jupiter. The second category includes Uranus and Neptune, the ice giants. Like Jupiter and Saturn, they have thick atmospheres composed of hydrogen and helium, but their overall composition contains far more heavy compounds called ice. These 4 planets are so large that between them, they account for over 99% of the mass orbiting the Sun. They are composed mainly of hydrogen, helium, and a little water. They have no solid or liquid surface, and should be thought of as balls of gas, where pressure and temperature increase as you penetrate deeper into the planet. Jupiter and Saturn were discovered quickly because they are so large that they are visible to the naked eye. Historians believe they were spotted as far back as 5,000 years ago by the Babylonians, at the same time as Mars, Mercury, and Venus. Uranus was detected in 1781 by a German-British astronomer, William Herschel. In the meantime, Galileo had popularized the use of instruments to observe the sky. Telescopes and refracting telescopes became invaluable tools for astronomers. The discovery of Neptune is attributed, after some debate, to the Frenchman Urbain Le Verrier, who did not observe it directly, but deduced its existence by calculation in 1846. The same year it was observed for the first time by German astronomer Johann Galle from the Berlin Observatory. The Voyager 1 and 2 probes were the first to fly over Uranus and Neptune. Launched in 1977, they benefited from the gravitational assistance of Jupiter and Saturn. They are still on their journey, albeit with increasingly distant signals. In 2017, the Juno probe revealed the detailed appearance of Jupiter. Uranus and Neptune were only flown over once in the 1980s. Only Jupiter and Saturn have been the subject of dedicated missions, with 3 probes, Galileo, Juno, and Cassini-Huygens, put into orbit. These 3 probes have provided us with a wealth of information on the gaseous planets. Galileo disintegrated in Jupiter's atmosphere on September 21, 2003. This programmed end by NASA prevented it from polluting the moon Europa, which we would like to study. Cassini plunged into Saturn's atmosphere, where it disintegrated in September 2017 for lack of fuel. Huygens stopped transmitting data after landing on Titan. Of these 3 probes, only Juno is still active. We've still got a little time to get there, and you'd like to know how they formed? It all started 4.6 billion years ago when the Sun formed. They were all born within the same cloud. In the beginning, a cloud of gas and dust collapsed under its own weight, forming a disk. The bulk of the matter concentrated in the middle, where the Sun was born. The remaining dust and gas continued to rotate in particular patterns. The heavier elements remained close to the Sun, in the center of the disk, while the lighter elements moved towards the periphery. These light elements are gas and dust. The dust met, and by accretion formed baby planets, called protoplanets, which can have 10 times the mass of the Earth. The mass of these protoplanets, made of rock and sometimes ice, begins to attract nearby debris. This debris includes the surrounding gases. The accumulation of these gases further increases their mass. The critical mass of the solid core is reached after 8 million years at around 15 Earth masses. Gas accretion then becomes exponential, and the protoplanet becomes a gas giant. It is this very mass that still enables gas giants today to hold these gases around them. The solid core provides the gravitational force needed to hold the gas envelope in place. Without it, the solar winds would have swept the gases away long ago. This explanation, known as the solid core explanation, is the one that currently prevails for the formation of gas giants. But the debate on the formation of gas planets is still far from settled. A second scenario is that of gravitational instability. Giant planets would form like stars. In 2023, astronomers may have observed the birth of a gaseous planet for the first time. Using the Very Large Telescope, they spotted dust clusters near a young star. The young star, V960 Mon, is located more than 5,000 light-years from Earth, in the constellation of the Unicorn. These clusters could collapse and give rise to giant planets. These observations lend credence to the second hypothesis. But now we're approaching the first and most famous gas giant, Jupiter. Let's take a step forward. We're already 778 million kilometers, or 485 million miles from the Sun, or 5.2 astronomical units. Jupiter is 2.5 times heavier than all the other planets in the solar system combined. It alone accounts for over 70% of the mass orbiting the Sun. It's huge. Its diameter is 142,800 kilometers, or 88,000 miles, which is 11 times that of the Earth. This power earned it its name, that of the Master of the Gods, who governed the sky, light, lightning, and thunder in Roman times. Galileo was the first to observe it in detail in 1610 and to discover 4 of its satellites. Today, when we observe it from space, we see bands of white clouds against a background of orange, red, or beige atmosphere, parallel to the planet's equator. These are gaseous masses carried along by the planet's rotation. The color of the gases depends on their altitude, and they are mainly hydrogen and helium, with small quantities of methane and ammonia. This atmosphere is 5,000 kilometers or 3,000 meters thick. If by magic an observer were to penetrate this planet's atmosphere, paleontologists believe he would sink without encountering any limits through a thick layer of gas, mainly hydrogen. Then gradually, it would pass through fluid layers, as if the air were gradually being transformed into water. In reality, it's liquid hydrogen and helium. Our visitor would eventually reach a hard layer, the planet's core, tiny in comparison to the planet's totality. This core would be close to Earth in diameter, 10 times more massive, and above all, extremely hot. It would reach 70,000 degrees Celsius, or 125,000 degrees Fahrenheit, 10 times hotter than the Sun's surface. Jupiter emits 1.5 times more heat than it receives from the Sun, yet its surface temperature is minus 161 degrees Celsius, or minus 258 degrees Fahrenheit. Astronomers have calculated Jupiter's rotation period as 9 hours, 55 minutes, and 30 seconds. Its period of revolution is almost 12 years. Jupiter's seasonal variations are extremely slight, as it rotates almost vertically. Jupiter fascinates not only by its size, but also by its restlessness. Its atmosphere is alive with powerful meteorological phenomena. Have you ever heard of the Great Red Spot? This gigantic storm has been observed for 350 years and remains a fascinating subject of study. It extends over less than 15,000 kilometers, or 9,300 miles in length. You could almost fit the Earth inside it. This year, 2024, the Hubble Space Telescope captured new images that revealed an unsuspected dynamic of this storm. Once seen as relatively stable, it is now known to change size and intensity on a regular basis. Scientists have described it as oscillating like a bowl of gelatin. In images taken over a 3-month period, the storm can be seen compressing and expanding while changing its speed. For the moment, no explanation has been put forward for this phenomenon, but scientists are keeping a close eye on it. But that's not all. The James Webb Telescope has also made a major discovery. Using its infrared spectrometer, it has revealed the presence of unknown atmospheric structures, such as dark arcs and points of light in the planet's upper atmosphere. The telescope's advanced instrumentation has made it possible to examine areas that were previously difficult to observe. This opens the way to new questions and theories about how giant storms form. The Juno mission not only studied the Great Red Spot, but also the planet's poles. It revealed something surprising. Giant cyclones organize in octagonal patterns. Strange and unexpected, don't you think? These formations have been stable for several years. They demonstrate an unexpected resilience. The cyclones interact with each other, gently oscillating around a point of equilibrium without ever losing their stability. This discovery could provide clues to the forces at work in the atmospheres of giant planets. Juno also explored the depths of Jupiter's winds. These extremely violent winds form the alternating bands seen in images of the planet. They reach depths of over 3,000 kilometers or 1,900 miles below the clouds, and speeds of up to 600 kilometers per hour or 370 miles per hour. This raises a new question. How are these winds formed, and why do they extend so deep? Jupiter is interesting not only for its own sake, but also for its satellites. It is thought to have 95 natural satellites, the best known of which are Io, Europa, Ganymede, and Callisto. Europa is of particular interest to astronomers as it is an excellent candidate for harboring life outside Earth. Scientists believe that an ocean of salty liquid water hidden beneath the ice could contain conditions conducive to life. On October 14, 2024, just a few weeks ago, NASA launched the Europa Clipper mission to study Europa. Europa Clipper is expected to map the satellite and search for signs of life by carrying out around 50 flybys. It is a 6-ton space probe, half of whose mass is made up of ergols, a substance designed to provide it with energy. The probe should reach its destination within 5 years. It will benefit from the gravitational assistance of Mars and Earth. It is scheduled to enter orbit around Jupiter in April 2030. The scientific phase will last 3.5 years. We already know that Europa's diameter is 3,130 kilometers or 2,000 miles. Its distance from Jupiter is 671,000 kilometers or 415,000 miles. Its period of revolution around Jupiter is 3.5 days. Europa is the smoothest body in the solar system. This Jovian satellite has a surface as smooth as a billiard ball. When meteorites smash into its frozen surface, they release a lava of water, which as it solidifies, erases all traces of the impact. It is entirely covered in ice. The European Space Agency has also launched a mission to explore the satellites Callisto, Europa, and Ganymede. Departing on April 14, 2023, the Jupiter Icy Moon Explorer is scheduled to arrive in 2031. But back to Jupiter. We haven't finished describing it yet. Like all gaseous planets, it has rings. Revealed by the Pioneer 10 probe in 1974, they are so faint that they are only visible against the light. As a result of the planet's gravitational influence, the particles have coalesced into a very thin disk. This ring system, photographed by Voyager, seems to be fed by dust from Jupiter's closest satellites. The most likely scenario for their origin suggests that these particles are produced by the relentless bombardment of meteorites on the smaller Jovian satellites, such as Metis, Adraste, Amalthea, and Thebe. Let's move on and approach Saturn. It's also named after a Roman god, the god of time. You're probably familiar with Saturn and its ring system, the most extensive in the solar system. When Galileo first saw them, he didn't know what they were. His first sketches give the impression that he had drawn ears on the planet. These rings are the most complex in the solar system. Their structure is extremely complex. 3 wide bracelets are easily distinguished, themselves made up of dozens of interlocking rings. They are not solid. Each ring is made up of particles containing 90% to 95% water ice. These particles range in size from dust grains to blocks 10 meters or 33 feet in diameter. The rings extend up to 300,000 kilometers or 185,000 miles from the planet. They are extremely thin, with an average thickness of 10 meters or 33 feet. Each ring rotates around the planet at a different speed. Between these rings are what is known as benevolent satellites. Like good shepherd's dogs, they use their gravitational influence to bring back any blocks that try to escape. The rings are named in alphabetical order, from A to G. The closest to the planet is the D ring, made up of ice particles and dust. The B ring, made of ice and water, is the brightest. The Phoebe ring takes its name from the eponymous satellite whose dust it collects. In October 2023, the Hubble telescope sent back images showing mysterious spots appearing and disappearing on the rings. How can they be explained? Scientists believe that the solar wind collides with Saturn's magnetic field, and at the stumbling blocks, the dust and ice shift. Solar winds are said to strike hardest at the equinox. Saturn's new season will give researchers 7 years to confirm this hypothesis. Unfortunately, these magnificent rings will disappear within 300 million years. This disappearance is due to the combined effect of the sun's ultraviolet radiation and plasma. Saturn is 1,427 million kilometers, or 890 million miles from the Sun, or 9.5 astronomical units. Its diameter is 120,600 kilometers, or 750,000 miles. Its surface temperature reaches -170 degrees Celsius, or -274 degrees Fahrenheit at first cloud. This beautiful planet has cloud layers similar to those of Jupiter. Its rotation stretches cloud formations into colorful bands, parallel to the equator. Its pale yellow hue comes from ice crystals composed of a chemical called ammonia in the upper atmosphere. Saturn is characterized by low density. Immersed in a bathtub its size, it would float. It also has an internal energy source 1.76 times more intense than the solar radiation absorbed by the planet. Its rotation period is 10 hours 33 minutes. Its period of revolution is 29 Earth years, and its orbital speed is 10 kilometers per second. Its axis of rotation is inclined at 26.7 degrees, giving rise to seasonal variations as on Earth. A Saturnian season lasts 7.5 Earth years. Saturn's eccentric, elongated trajectory means that when it's close to the Sun, its atmosphere is the scene of storms, with winds of up to 2,000 kilometers per hour, or 1,240 miles per hour. One of the best-known storms is the Great White Spot. This storm, located in Saturn's northern hemisphere, occurs every Saturnian year, i.e. every 29 Earth years. It can extend over thousands of kilometers and last for several months. About 10 flashes of lightning burst every second. The first storm was observed in 1876. The Cassini probe observed the sixth in 2010. Its head was around 7,000 kilometers, or 4,400 miles in diameter, followed by a long trail that almost circled the planet. It lasted almost 7 months, accompanied by lighting up to 10,000 times more intense than terrestrial lighting. The formation of these large spots is not yet fully understood. Researchers believe that hot water vapor rises and reaches colder layers, triggering the storms. Saturn, like its neighbor Jupiter, contains a small core at its center. This dense core is composed mainly of silicates, iron, and other heavy elements. Although hidden by the planet's massive outer layers, the core is thought to measure around 6,000 kilometers, or 3,800 miles in radius, and represents the gas giant's hottest and densest region. The temperature here reaches around 11,700 degrees Celsius, or 21,000 degrees Fahrenheit, and the pressure is unimaginable, compressing materials into an exotic state. Surrounding this core is a thick layer of liquid metallic hydrogen stretching for some 20,000 kilometers, or 12,500 miles. Here, under gigantic pressure, more than 3 million times the Earth's atmospheric pressure, the normally gaseous hydrogen is transformed into a conductive liquid. This layer is essential as it generates Saturn's powerful magnetic field, which protects the planet and its moons from the charged particles of the solar wind. Above this metallic region, another layer of liquid molecular hydrogen and helium takes its place. This zone, some 17,800 kilometers, or 11,800 miles thick, marks the transition to the outer parts of the planet. It is characterized by a fascinating phenomenon. Helium droplets condense and fall like rain to the depths, enriching the lower layers and releasing heat. Finally, enveloping everything is Saturn's visible atmosphere, a layer of gas around 1,000 kilometers, or 620 miles thick. Consisting of 93% molecular hydrogen and 7% helium, it also contains traces of methane, ammonia, and water. This region is the scene of Saturn's emblematic cloud bands and storms. These very high temperatures and pressures make hydrogen electrically conductive, generating a powerful magnetic field 500 times greater than that of Earth. Scientists have a hard time measuring the difference between the inclination of the magnetic field axis and that of Saturn's rotation axis. It doesn't work like on Earth, where the two axes are at an angle of 11.2 degrees. Perhaps you've heard that it rains diamonds on Saturn? It seems that around 1,000 tons of diamonds rain down on Saturn every year. The storms I mentioned earlier are powerful enough to break up the methane molecules in the atmosphere. This would give rise to simpler particles of carbon, soot. This would fall through the atmosphere until it reached a denser zone where, under high pressure, it would turn into graphite. As it continues to fall, this graphite is transformed into solid diamond. As it falls, it hardens into pieces of graphite, then into rare diamonds. But don't expect to pick them up, as these diamond hailstones would eventually melt into a liquid sea of lava in the planet's hot core. On the other hand, they would certainly remain in a solid state on Uranus or Neptune. For years, scientists have been searching for moons around Saturn. In May 2023, the work of an international team of astronomers led to the discovery of 62 new moons. Saturn thus regained the lead in the race for moons around giant planets. Dr. Ashton's team used the displacement and stacking technique, never before used around Saturn. The aim is to find moons that are less and less luminous and smaller. By moving and stacking many sequential images taken over 3-hour periods, the team detected moons as small as 2.5 kilometers or 1.5 miles in diameter. The data were collected using the Canada-France-Hawaii telescope. The moons had to be tracked for several years to ensure that they were natural satellites and not asteroids. It had to be established that these objects were in orbit around the Sun. All these moons belong to the class of irregular moons. They are thought to have been captured long ago by the host planet, but to have formed elsewhere. They are characterized by wide, elliptical, and inclined orbits. With these new moons, there are now 146 recognized moons around Saturn. Saturn's irregular moons fall into three groups: Inuit, Celtic, and Nordic. The Nordic group is the most populous. Bestla, discovered in 2004, is a good example of a moon belonging to the Nordic group. It orbits Saturn at an average distance of 20 million kilometers or 12 million miles. It completes a full revolution around Saturn in almost 1,000 Earth days at a speed of 4,595 kilometers per hour, or 2,900 miles per hour. Its diameter is around 7 kilometers or 4 miles, and its circumference 22 kilometers or 14 miles. The study of irregular moons reveals the final phases in the formation of the solar system. Saturn's best-known satellite is Titan, discovered in 1655 by Dutch astronomer Christian Huygens. It is very large, 1.5 times the size of the Moon. Its diameter is 5,150 kilometers, or 3,200 miles. Its distance from Saturn is 1,220,000 kilometers, or 760,000 miles. Its period of revolution around Saturn is almost 16 days. Titan alone accounts for 96% of the mass orbiting the planet. It is massive enough to retain an atmosphere. In fact, it is the only known satellite to have a dense atmosphere. This atmosphere, composed of nitrogen and methane, gives the planet a beautiful orange color. Titan is said to resemble the Earth as it was billions of years ago. The Cassini and Huygens probes have discovered dunes, canyons, and mountains. They have also discovered rivers, lakes, rain, and clouds. But it's not water that's flowing, but methane. And then there's the famous underground ocean that has piqued the curiosity of researchers still searching for extraterrestrial life. This liquid ocean lies 60 kilometers or 37 miles beneath Titan's icy surface. According to Cassini measurements, it is composed of a mixture of water, ammonia, and other constituents. This ocean would rest on ice. There is therefore little chance of life emerging in this internal ocean with no source of heat. Recently, however, researchers have turned their attention to another of Saturn's satellites, Mimas. Star Wars fans will have recognized the black star from the film in its atypical physique. A huge crater called Herschel can be seen on the satellite's surface. Its diameter is 130 kilometers or 80 miles, which is impressive when you consider that the diameter of Mimas is around 400 kilometers or 250 miles. It too contains an ocean hidden beneath its surface, but only 20 kilometers or 12 miles deep. This is a surprising discovery, as we never expected to find an ocean in such a small celestial body. Once again, it was the Cassini probe that made this discovery possible. The ocean is thought to have formed recently, between 5 and 15 million years ago, and to have reached its present depth only 2 to 3 million years ago. NASA and ESA have been planning programs for years to explore the underground oceans of Enceladus or Europa. I told you about Europa earlier. Here are some facts about Enceladus. Enceladus is Saturn's sixth icy moon. It harbors the 6 elements essential to life, including phosphorus, the rarest of them all. So as you can imagine, it's getting very interesting too. The other 5 elements are carbon, hydrogen, nitrogen, oxygen, and sulfur. Enceladus is just 505 kilometers or 310 miles in diameter. Scientists thought it was just an icy ball, until Cassini detected plumes of water vapor, again revealing the existence of a hidden ocean. NASA's Dragonfly project plans to send a drone to Titan's surface in 2028, arriving 6 years later in 2034. Weighing 450 kilograms, the drone will search for clues to hypothetical life forms. This year, NASA is finalizing another project, a robot that moves like a snake and is therefore able to cover all types of terrain. Called EELS, Exobiology Extant Life Surveyor, it could be sent to Enceladus. The trip would take 12 years. We're getting further and further away from Earth. We are now about 3 billion kilometers or 2 billion miles from the Sun. The Voyager 2 probe took over 9 years to reach it. It was astronomer William Herschel who discovered Uranus in 1781, when it was thought that the solar system was limited to 6 planets. Uranus and Neptune are known as icy giants. With a diameter of 51,000 kilometers, or 32,000 miles, Uranus is 4 times larger than the Earth. Can you understand why it's called a giant? When you look at Uranus, you see a large ball with a blue-green hue, rather faded. This strange color is probably due to the presence of methane in its atmosphere. Methane is a gas made up of carbon and hydrogen. At its center is an Earth-sized core of silicate rock, iron and nickel. This core is surrounded by a mantle of volatile components called ices, despite their state between liquid and solid. This mantle, some 10,000 kilometers or 6,200 miles thick, is made up of water, ammonia, and methane. All this is enveloped in an atmosphere made up of the same ingredients, plus helium and hydrogen sulfide. This last gas has caused quite a stir, because it smells like rotten eggs. Researchers therefore found it amusing to say that Uranus smelled bad. Icy giants have a mass well below that of Saturn or Jupiter, but represent 10 to 15 Earth masses. The mass of Uranus is 14.5 times that of our planet. Only 20% of this mass is hydrogen, whereas on Saturn, hydrogen accounts for 90% of the mass. A large part of Uranus's mass is stored in its ices. Its rotation time is 17 hours. Its revolution time is 84 years, and its orbital speed is 7 kilometers per second, or 4 miles per second. It holds the record for the coldest atmosphere in the solar system, reaching minus 224 degrees Celsius or minus 371 degrees Fahrenheit. Why it is the coldest planet in the solar system is not entirely clear. Some think it's because of its tilt, while others suggest that its core cooled during the Great Collision I'll tell you about in a moment. Uranus has a curious feature. It is literally lying on its trajectory. While the other planets spin like tops, Uranus rolls like a ball in the plane of its orbit. As a result, each of Uranus's poles faces the Sun for 42 years at a time. It is thought that when Uranus was young, between 3 and 4 billion years ago, it was hit by a large celestial body which tipped it over. Some call it the planet in bed. The temperature differences between the light and dark sides of the planet create a very strange meteorology, completely different from that of other planets. The encounter with this celestial body could also explain its retrograde rotation. Like Venus, it rotates in a clockwise direction, unlike all the other planets. Uranus has only been visited once by Voyager 2 in 1986. The flyby lasted 5 hours and 30 minutes, just 80,000 kilometers or 50,000 miles from the planet. The probe observed the planet's rings. Since then, Uranus has not been one of NASA's priority missions, but that's about to change. A new mission called Uranus Orbiter and Probe is underway. The launch is scheduled for 2031, but the probe will not orbit the planet until 2044. It will study the structure and origins of the planet, as well as the nature and formation process of its rings. Uranus has 13 dark-colored rings. They represent the second largest ring system discovered after that of Saturn. Composed of ice and minerals such as carbon, they measure less than 150 meters or 500 feet thick. They are therefore particularly narrow, especially when compared to their circumference of over 260,000 kilometers or 160,000 miles. The Hubble Space Telescope revealed the two outermost rings in 2007, when the planet tilted in such a way that from Earth its rings overlapped. The first rings were discovered in 1977. Their dark color is certainly due to their composition: ice and organisms blackened by radiation from the magnetosphere. Most of Uranus's rings are opaque and relatively narrow, measuring just a few kilometers across. The ring system is distinguished by its low dust content, being made up mainly of boulders up to 20 meters or 65 feet in diameter. The rings are named Zeta, Alpha, Beta, Eta, Gamma, Delta, Lambda, Epsilon, Nu, Mu, and 6, 5, 4. Mu, the outermost ring of Uranus, has an attractive blue color, as does the outermost ring of Saturn. Astronomers believe that these satellites act as filters, capturing the ring's larger particles while allowing smaller ones to pass through. These particles, smaller than a micron, would scatter blue light. The new ring, close to Mu, has a beautiful red color. Uranus has 28 known natural satellites. They are named after characters in the works of William Shakespeare and Alexander Pope. The 5 major satellites of Uranus are Titania, Oberon, Miranda, Ariel, and Umbriel. The first 2 were discovered by William Herschel 6 years after his discovery of Uranus. The others were discovered at different times, either by astronomers or by ground-based telescopes. Titania is the largest moon of Uranus, with a diameter of 1,578 kilometers or 980 miles. This is half the diameter of our moon. Like our moon, it always shows the same face to its planet. Titania's reddish surface is covered with canyons, scars, and numerous impact craters. The 28th moon was recently discovered in November 2023 in images provided by the Magellan Telescope in Chile. A bright spot can be seen, the new moon S2023. It is only 8 kilometers or 5 miles in diameter. It takes 680 days to complete its orbit around Uranus. Its eccentric, distant, and inclined orbit suggests that it was captured by the planet's gravity during or shortly after its formation. A better understanding of how these moons were captured may help astronomers better understand the early years of our solar system. All the major moons of Uranus are composed of equal parts of rock and ice, except Miranda, which is composed mainly of ice. This ice may contain ammonia and carbon dioxide. A recent study suggests that Miranda may have sheltered an ocean of water, the remains of which are still hidden beneath its surface. Scientists estimate that this ocean was at least 100 kilometers or 62 miles deep. This is enormous compared with our oceans, whose maximum depth is around 11 kilometers or 7 miles. It is thought that some water remains beneath Miranda's surface, because if it had frozen completely, there would be cracks in its surface. However, the researchers cannot see any cracks in the images available to them. This is yet another hope for finding traces of extraterrestrial life. What's more, researchers believe that other moons like Ariel or Titania could also be hiding a secret ocean. You're likely to hear more about this little-known planet in the next 10 years or so. In the meantime, Uranus is visible in our skies right now. From January 30th, 2025, it will move backwards again. But now we're getting a glimpse of the planet furthest from the Sun, Neptune. You'll remember that the discovery of Uranus came as a surprise to astronomers. They thought they discovered all the planets in the solar system, and then there was another one. This latest discovery gave them renewed motivation. What if there were more planets out there? So they began to scan the sky again, except for Urbain Le Verrier, who preferred to rely on mathematics and calculation. In September 1846, he indicated the possible position of the eighth planet to the German Johann Galle. Galle found the planet immediately. Far more distant than Uranus, Neptune is nevertheless better known thanks to the Voyager 2 probe, which sent us some superb photographs in 1989. Its distance from the Sun is 4.5 billion kilometers or 2.8 billion miles. It is never visible to the naked eye. A telescope is essential to see it. Voyager 2 reached Neptune after a long journey of 12 years. It benefited from gravitational assistance, and its journey continues to this day. The probe passed within 4,950 kilometers or 3,000 miles of the planet's North Pole on August 25, 1989. Such a close passage made it possible to use gravitational assistance once again and continue on to Triton, Neptune's main moon. Initial observations in March 1989 revealed Neptune's rings. 9 new moons were also discovered during this mission, but it was not possible to organize detailed observations of them. Only Proteus was discovered in sufficient detail to make it possible to plan its observation. Let's take a closer look. Neptune has a beautiful blue color due to atmospheric layers rich in methane. With a diameter of 49,500 kilometers or 30,800 miles, it is the smallest of our 4 gas giants. Its mass is 17.2 times that of the Earth, making it the 3rd most massive planet in the solar system. Its mass is only 1/19 that of Jupiter, yet it is the densest giant planet in the solar system. Its revolution lasts 165 years, and its rotation only 16 hours. The temperature observed at the cloud tops is minus 218 degrees Celsius, or minus 360 degrees Fahrenheit. Its clouds are composed of frozen methane and contain fewer water ice crystals than our own. It has a permanent cyclonic formation containing a secondary white cyclone, nicknamed the Scooter. It's not the noise that earns it this nickname, but its speed. It circles the globe in 16 hours. Storms come and go around Neptune at over 1,600 kilometers per hour, or 1,000 miles per hour, peaking at 2,100 kilometers per hour, or 1,300 miles per hour. Take a close look at the photos taken by Voyager 2. See that darker spot? Voyager 2 discovered it in Neptune's southern hemisphere. Researchers nicknamed it the Great Dark Spot. At first, they thought it was a cloud formation before agreeing that it was a hole between clouds. The dark spot disappeared in November 1994. It is thought to have dissipated due to excess heat, or to have been covered by other cloud layers. Even faster clouds were discovered in other images, such as the little dark spot, which rotates in a clockwise direction. I don't know if small is the right word for it, as it's still wider than the Atlantic Ocean. As Voyager 2 approached it, a small shiny heart appeared. This too has since disappeared. But before it disappeared, it behaved strangely. Dark vortices, as researchers call them, appear at mid-latitudes before heading towards the equator and disintegrating. But in 2020, our little dark spot decided to head back north. Never before seen. How can this be explained? Astronomers noticed that at the moment of this change of direction, a smaller spot appeared next to the larger one. They believe that this junior dark spot is a fragment of the larger one. By breaking off, this fragment could have disrupted the dynamics of the initial vortex, causing it to change course. But while some disappear, new spots appear. This seems normal for a storm. We can observe them from Earth, thanks to the VLT, or Very Large Telescope. The Hubble Space Telescope captured images of several dark spots in 2018. The VLT's Multi-Unit Spectroscopic Explorer, MUSE instrument, broke down the sunlight reflected by Neptune in its spot into different colors or wavelengths. The result is a 3D spectrum. This spectrum provided clues as to the chemical composition of the various layers of the atmosphere and explained why the spot appeared dark. The hole in the clouds hypothesis gave way to another. The dark spots were thought to be the result of air particles darkening in a layer beneath the main visible haze layer when mists and ices mix. And the researchers had another pleasant surprise: the discovery of a rare new type of deep bright cloud. This new cloud is at the same level as the main dark spot. It's a completely new cloud, and a very exciting one at that. You'll have to wait for the results of scientific observations to find out more. The good thing is that today they can observe all this from Earth, and don't need to send a probe as far. Let's face those storms and get closer to Neptune's body. Neptune's internal structure is similar to that of Uranus. It probably has a solid core of iron, nickel, and silicates. The pressure at the center of this core would be twice as high as at the center of the Earth, and the temperature would be around 8,000 degrees Celsius, or 14,400 degrees Fahrenheit. Above this core, it could have a fairly uniform composition of different ices, hydrogen and helium. This sets it apart from Jupiter or Saturn, which have a layered structure. Today's several models for the structure of Uranus or Neptune propose a three-layer arrangement: a solid core, a middle layer made up of water, methane, and ammonia, and an atmosphere composed of hydrogen and helium. But there is still no certainty about Neptune's exact composition. It's so far away. We do know, however, that its atmosphere is more than 8,000 kilometers or 5,000 miles thick. It is 85% hydrogen, 13% helium, and 2% methane. Its internal heat is sufficient to generate the fastest planetary winds in the solar system. Neptune's temperature is not stable. Variations of several degrees have been observed from one year to the next, thanks to images provided by the Very Large Telescope. These variations are still unexplained. Neptune is surrounded by a system of 5 rings, some of which display very bright concentrations of matter. These rings were discovered indirectly in 1984 from Chile. This led to changes in the Voyager 2 program so that the rings could be studied more closely. At first, it was thought that they were not complete, but Voyager 2's passage allowed us to see them in their entirety and discover that certain parts were brighter. These brighter parts were in fact what researchers had mistaken for arcs. One of the rings, called Atoms, has 4 arcs nicknamed Liberté, Égalité, Fraternité, and Courage. Scientists believe that these arches are locked into their shape by the effects of the moon Galatea. Some of them are twisted, but we don't yet know why. The 3 main rings are Gal, located 41,900 kilometers or 26,000 miles from Neptune's center, 2,000 kilometers or 1,200 miles wide. Leverrier, which lies 53,200 kilometers or 33,000 miles from Neptune's center and is very narrow, being only about 113 kilometers or 70 miles wide. Lassell, which lies 53,200 kilometers or 33,000 miles from the center of Neptune and is 4,000 kilometers or 2,500 miles wide. The latter is bounded by Arago, which lies 57,200 kilometers or 35,000 miles from the center of Neptune and is less than 100 kilometers or 60 miles wide. Arago is not always distinguishable from the Lassell ring. Leverrier, Arago, and Atoms are narrow, up to 100 kilometers or 60 miles wide. You'll notice that there are big differences in width between the rings. These rings are thought to be young, formed after the solar system. They were probably formed by the fragmentation of former inner moons during collisions. They contain a large amount of dust, making them similar to Jupiter's rings. The particles are made of dark material, probably a mixture of ice and organic compounds transformed by radiation. 3 moons orbit the rings: Naiad, Thalassa, and Despina. Neptune has 16 known natural satellites. As Neptune is the Roman god of the sea, his satellites are named after lesser marine gods. Triton, discovered in 1846, is a large satellite, 2,700 kilometers or 1,800 miles in diameter. It is therefore larger than Pluto. It orbits 355,000 kilometers or 220,000 miles from the planet and comprises more than 99.5% of the mass orbiting Neptune. It is massive enough to undergo gravitational compression and be spheroidal. Its surface is relatively young, with very few visible craters. There are numerous ridges and valleys, no doubt the result of freeze-thaw cycles. But the most interesting feature is its volcanic activity. It spews out plumes of ice. An image taken by Voyager 2 shows an erupting plume 8 kilometers high and carried 140 kilometers, or 87 miles, by the wind. The material spewed out is probably liquid nitrogen, dust, or methane compounds from beneath the surface. This activity regularly modifies its surface, making it the second youngest planet in the solar system. Strangely enough, it orbits the planet in the opposite direction to all the other satellites. This peculiar motion suggests that it is a former dwarf planet, originating from the Kuiper Belt and reclaimed by Neptune. It orbits Neptune in 5 days and 21 hours on an almost circular trajectory. Its inclination gives it very marked seasons throughout the Neptunian year. Triton is the coldest object ever observed in the solar system with temperatures of minus 235 degrees Celsius or minus 391 degrees Fahrenheit. Its atmosphere is composed mainly of nitrogen and a small amount of methane. All we know about Triton comes from the Voyager 2 probe, the only one to have approached it in 1989. It will eventually break up when it reaches the Roche limit in 3.6 billion years' time. Nereid was discovered in 1949. It is the third most massive moon in the Neptunian system. Its surface is highly irregular, resembling a large oval pebble full of craters. It has one of the most eccentric orbits in the solar system. Its apoapsid, maximum distance from Neptune, is 7 times greater than its periapsid. Bestla, a natural satellite of Saturn, beat this record in 2004. Larissa was discovered in 1981 thanks to a star occultation. It is riddled with craters but shows no geological activity. Its average radius is around 97 kilometers or 60 miles, as its shape is irregular. It is heading slowly towards Neptune and will disintegrate as it crosses the Roche boundary. Next, photos transmitted by Voyager 2 introduce us to Naiad, Thalassa, Despina, Galatea, and Proteus. Naiad is Neptune's closest natural satellite. It orbits at an average distance of 48,000 kilometers, or 29,900 miles. It orbits in a spiral, slowly approaching the planet. It should break up as it crosses the Roche boundary. Thalassa is very small, no more than 80 kilometers or 50 miles in length. There is no geological activity. Despina and Galatea are quite similar, but a little larger, with lengths of around 150 kilometers or 93 miles. Proteus is one of the darkest objects in the solar system, almost as dark as soot. Like most moons of gaseous planets, it reflects only 10% of the light that strikes it. 5 new moons were discovered between 2002 and 2003, and named in 2007: Psamathe, Halimede, Sao, Laomede, and Neso. Psamathe is a tiny satellite estimated to be just 38 kilometers or 24 miles in diameter. It orbits Neptune at an average distance of 46,700,000 kilometers, or 29 million miles in 25 years. Neso is Neptune's furthest satellite. A complete orbit of the planet takes 26 years. Finally, in 2013, Hippocampus was discovered by combining several Hubble images. It is the smallest moon known to date. Its width is no more than 21 kilometers or 13 miles. It wasn't easy to find. Planets, whether gaseous or rocky, also have small bodies called Trojan asteroids. A Trojan is an asteroid, sometimes a moon, sharing the same orbit as a planet or one of its satellites at stable points. These points are called Lagrange points, L4 and L5. They lie 60 degrees ahead or behind the main object. The first Trojan asteroid was discovered in 1906 near Jupiter. It illustrates the theory of Pierre de Lagrange, who demonstrated as early as 1772 that when 2 celestial bodies orbit each other, there are 5 points in the orbit where gravitational force compensates for centrifugal force, and where a 3rd celestial body remains stationary relative to the other 2. But only points L4 and L5 give rise to truly stable orbits. Passing through these 2 precise points prevents asteroids from colliding with the main body around which they orbit. Since 1906, thousands of Trojan asteroids have been discovered. Mars has 16, Neptune 32, but Jupiter has thousands, over 7,000. These asteroids are named according to their position. If they precede the planet, they are named after a hero from the Iliad. If they follow it, after a Trojan hero. In the end, the term Trojan asteroid covers both cases. Most of them are up to 200 kilometers or 125 miles in size. But in 2011, Canadian researchers discovered a Trojan orbiting the Earth with a diameter of just 300 meters or 1,000 feet. NASA launched a space probe on October 16, 2021 to study 6 Trojan asteroids on Jupiter. Lucy, as the probe is called, is scheduled to fly over them between 2027 and 2033. It will be the first spacecraft to approach them. They are small, dark, and very far from Earth, which explains why they have not yet been studied. Observing them may enable us to validate the NICE model, a scenario describing the formation and evolution of the solar system. According to this scenario, developed in 2005, gas giants originally occupied orbits much closer to the Sun. It would be during this period that asteroids from the entire solar nebula would have settled at points L4 and L5. But how did these objects get there? It is thought that they were initially located in different parts of the solar system, some of them in the Kuiper Belt. The movements of the gaseous planets would have moved them to the Lagrange points of the planet Jupiter from the earliest ages of our solar system. They are composed of primitive materials that aggregated during the formation of the solar system. In a way, they are fossils of the formation process. Jupiter's Trojan asteroids circulate in the same orbit as Jupiter, around the Sun. They make up a group of several thousand bodies over 1 kilometer in diameter. But the Hector asteroid is much larger, measuring 370 kilometers or 230 miles. It is the largest known Trojan asteroid. It was discovered in 1907. In 2006, astronomers took a closer look at Hector with a 10-meter or 30-foot telescope located in Hawaii. The images confirmed a dual form that had already been suspected. Hector would be a binary asteroid whose 2 components would be bound together by gravitational forces. But the observations also revealed the presence of a small moon, Scamandrios. It's 15 kilometers or 9 miles long and lies around 1,000 kilometers or 620 miles from the asteroid. As I said, Jupiter has a large number of Trojans, including Nestor, Priam, Agamemnon, and Practol. Lucy should fly past Practol and its moon, Menicios, in March 2033. Together, these asteroids form 2 elongated clouds, centered on the 2 Lagrange points. There are currently 2 hypotheses about the fate of gas giants. The first hypothesis suggests that once the Sun has exhausted its reservoir of hydrogen, it will end its life as a white dwarf. As it becomes a compact, dimly lit star, its gravity will drop considerably, no longer able to hold planets in their current orbits. In time, these wandering worlds could be torn from their trajectories by the gravitational influence of passing stars, scattering the solar system across the vastness of the universe. Another, more recent hypothesis evokes the idea of planets becoming new planets, called Chthonians. This hypothesis was born after the discovery of the planet Osiris in 2000 in the constellation Pegasus. It's a gaseous planet that resembles Jupiter, but rotates much closer to its star. It is so close that the gases that make up its atmosphere are evaporating and could disappear in a few million years. All that would remain would be the solid core, resembling a telluric planet. It is this core that would be a Chthonian planet. Some scientists believe that the exoplanet Corot 7b could be the first Chthonian planet discovered. Other giant exoplanets are being studied to see if they belong to this new category. Space research is concentrated mainly outside our solar system. Having discovered the 8 planets of the solar system and their moons, we are now seeking to discover other, more distant planets or celestial objects. Several observation campaigns are underway, and the arrival of a new generation of instruments is opening the way to many new discoveries. The Hubble Space Telescope, operational since 1990, has increased our knowledge of exoplanets, black holes, and the expansion of the universe. The James Webb Telescope, to be launched in 2021, operates mainly in the infrared. A number of missions are already underway, such as Gaia, with more to come. The Plato mission will be launched in 2028. On Earth, too, instruments are becoming increasingly sophisticated. The world's largest radio telescope is called ALMA. With its 66 antennae, it provides us with new insights into the formation of the universe. It has the capacity of a telescope 14 kilometers or 9 miles in diameter. It can see 100 times better than any group of telescopes. The very recent VLT, Very Large Telescope, is the flagship of European astronomy. All these high-tech instruments have already enabled us to discover planets outside the solar system, exoplanets. Today, we have already located 7,360 of them. That's a huge number compared with the 8 planets in our own solar system. The number is growing at a dizzying pace. Most of them are very large gaseous planets. Their properties are very different from those of Jupiter and its neighbors, like Osiris, which I mentioned a moment ago. In 1994, Michael Mayor and his students spotted the first exoplanet, 51 Pegasi b. Not only is it a giant planet resembling Jupiter, it also belongs to a category of planets with no equivalent in the solar system, hot Jupiters. It orbits just 7.5 million kilometers or 5 million miles from its star. Hot Jupiters, which have now been studied for 25 years, are defined by a mass and size close to those of Jupiter and a period of revolution of less than 10 days. Hot Jupiters are easy to detect thanks to the transit technique. Hot Jupiter WASP 121b has a rotation period of 1.3 days. Its surface temperature can reach 2,500 degrees Celsius, or 4,530 degrees Fahrenheit. This is 5 times hotter than Venus, the hottest planet in the solar system. Hot Jupiters rotate synchronously with their star, so they always present the same face, the other being plunged into darkness, like the moon around the Earth. Scientists estimate that over time, the gases enveloping these boiling planets will evaporate under the effect of solar winds. All that remains is a rocky core. The study of these planets would help us to better understand our 4 gas giants. There are also warm and cold Jupiters. Saturn, Neptune, Jupiter, and Uranus are cold Jupiters. There are even super Jupiters whose mass is greater than that of Jupiter. As you can see, the universe still has a lot to teach us. We'd love to see what's out there. Only time and technological progress will allow us to travel deeper into the universe. But now our journey around the 4 gas planets is coming to an end. We're already on our return journey. Here are Neptune and Uranus, the majestic blue giants slowly fading behind us, taking with them the mystery of the icy confines. Ahead of us, Saturn's rings dance and sparkle, revealing themselves in a celestial embrace as we brush past them at full speed. Already Jupiter rises in all its grandeur. Its great red spot gyrates eternally, surrounded by its faithful moons that keep silent vigil. Farther away, Mars, our fiery neighbor, glows a deep red, witness to the secrets of the past. And finally, over there, at the center of our gaze, our precious Earth appears. Our beautiful blue planet, bathed in light, patiently awaits our return. Alpha Centauri A and B form the main binary star. These two stars, which shine brightly like our Sun and bear a striking resemblance to it, are easy to spot. More traditional names have been attributed to these stars, depending on their location. Alpha Centauri A was christened Regal Centaurus, which to Arab astronomers means the foot of the centaur. As you can see, this star, the brightest in the Centaur constellation, marks the location of one leg of this mythological creature, half horse, half man. Its companion, Alpha Centauri B, was named Ptoleman, which translates as ostriches. The origin of this choice of name remains a mystery. Finally, Alpha Centauri C, the third star to be discovered, owes its common name Proxima Centauri to its proximity to our solar system, literally meaning the nearest centaur star in Latin. Let's take a look at how these three stars are organized. The initial duo is made up of two main sequence stars, one a G-type star like our Sun, of almost identical age, and the other a K-type star. This means that Alpha Centauri A bears a striking resemblance to our Sun, also categorized as G2 V-type. But, unlike our Sun, this star has around 10% more mass and a 22% larger radius. Its luminosity is also estimated to be almost 50% greater. The secondary star is of spectral type K1V, hence its slightly orange luminosity. Slightly smaller and cooler than its counterpart, Alpha Centauri B has a mass around 90% that of the Sun and a diameter around 14% smaller. Its luminosity, also lower, is estimated at 0.445 times that of the Sun, with an apparent magnitude of plus 1.35. Both stars have an orbital period, slightly eccentric, that spans almost 80 years. When the two stars are at their closest, 11.2 astronomical units separate them before they continue their course, moving a maximum of 35.6 astronomical units apart. To give you an idea of their maximum distance at aphelion, this is equivalent to the distance between the Sun and Pluto. But if you'd like to have the privilege of observing these two stars as they come closer together, see you in May 2035. As far as Proxima Centauri is concerned, it took a long time for it to be confirmed as part of the original system, and with good reason. This faintly luminous star follows a much more distant orbit than the sparkling duo, the period of its orbit having been estimated at around 600,000 years. Its trajectory takes it 10,000 times further away from its companion stars than the distance separating our Earth from the Sun. This is why it took scientists long periods of observation before concluding that this red dwarf is indeed gravitationally linked to the Sun. Astronomers believe that the red dwarf was caught up in the luminous duo as it passed by. Moreover, the proper motion of Alpha Centauri AB's center of mass is estimated to have a radial velocity of 22.4 kilometers per second, or 14 miles per second, in the direction of our Sun. This double system, dragging Proxima along with it, is therefore insidiously approaching us, and will occupy various positions in our night sky as it slowly advances. Brighter and brighter it will reach the Hydra constellation in 27,700 years' time, coming ever closer to our Sun at around 3 light-years. Its apparent magnitude should then reach its peak, rivaling that of Canopus, the second brightest star after Sirius. Because of its relative proximity to our solar system, Alpha Centauri is a fascinating object of study for scientists. In fact, it is the site of numerous discoveries, each more exciting than the last, including the detection of candidate or confirmed planets in the vicinity of these stars. The system's main duo, Alpha Centauri A and B, could well harbor this type of object, but no confirmation has yet been provided. This hypothesis is all the more plausible given that no brown dwarfs or gas giants have been detected in the vicinity of this stellar pair, reinforcing the idea that a rocky planet could have formed there, at least in theory. According to astrophysicists, there could be a 75% chance that a telluric planet, and a potentially habitable one at that, could exist in such a system. In 2021, a planet orbiting Alpha Centauri A was suspected. This exoplanet candidate 1, estimated to be between the size of Neptune and half a Saturn, has an orbit approximately 1.1 astronomical units from the star, which it would cover in 1 year. As yet, this exoplanet has not been confirmed. Although the idea that it could be a background star has been dismissed, it could just as well be a dust disk, or even an artifact. Alpha Centauri B is no match for its close neighbor. It too seems to be accompanied by a planetary object. In October 2012, the sighting of a planet was announced by a Swiss astronomer. Named Alpha Centauri BB, this object, probably a telluric planet the same size as our Earth, is said to be experiencing terrible conditions. With an orbit very close to its star, and a period of revolution of just 3.2 days, one of its faces must be locked and constantly exposed to the 1,000 degrees Celsius or 1,800 degrees Fahrenheit of its sun. Since this statement, numerous studies have disputed the existence of this potential planet, including computer simulations. Although the actual existence of this candidate planet is in question, this challenge does not amount to a certainty either. In March 2015, another candidate planet was announced orbiting Alpha Centauri B, this time by a French astrophysicist. Slightly smaller in size than our Earth, this planet would also be too close to its star, although its orbit would last less than 20 days, and therefore be slightly wider. If the existence of this planet, named Alpha Centauri BC, were to be confirmed, it would unfortunately be unable to contain liquid water on its surface. Finally, it was with Proxima, the distant companion system, that not one, but 3 planets were detected for the first time. In August 2016, a team from the European Southern Observatory made this incredible announcement. Proxima Centauri B is the first confirmed exoplanet in this vast system. Probably telluric, this exoplanet has a mass at least equivalent to 1.3 Earth masses, and its radius could be 10% greater. What's more, its orbit, which it completes in 11.18 days, places it in the habitable zone of its host star, the system's sole red dwarf. Interesting, isn't it? 3 years later, in 2019, a second planet was detected in Proxima's vicinity. Potentially a cold super-Earth or mini-Neptune, this exoplanet, named Proxima Centauri c, has a minimum mass of around 5.8 times that of Earth. It has an orbital period of just over 5 years, a long period that is of course attributed to its distance from its star, which is around 1.5 astronomical units. Although its existence was initially questioned, it was confirmed in 2020 by Hubble telescope recovery images dating back to 1995. Finally, an official announcement in February 2022 confirmed the existence of a third planet orbiting Proxima. This is Proxima Centauri d, a surprising exoplanet with one of the lightest masses for this type of object, only a quarter the mass of our Earth. Located just over 4 million kilometers or 2.5 million miles from its star, this exoplanet takes just 5 days to complete a full orbit. Although located in the hot zone, it is unfortunately not in its habitable zone. However, if its average temperature is estimated at 87 degrees Celsius or 190 degrees Fahrenheit, it could well be that these polar zones present more moderate, even welcoming temperatures. In short, this exoplanet could be home to large expanses of liquid water. In other words, oceans. Not all the observations made within this star system concern planetary-type objects. In 2017, a study carried out using the vast array of antennas at the Chile-based ALMA Observatory revealed that radiation from cold dust had been detected all around the Proxima star. According to the Spanish team, led by Guillem and Glada, the Proxima star is surrounded by cosmic dust rings. Composed essentially of particles of rock and ice that have not yet agglomerated to form a planetary object, these are not unlike the asteroid belts in our own system. Located beyond the orbit of the Proxima b planet, 2 dust-laden belts seem to encircle the star and its planet. The first appears to be 1 to 4 astronomical units away from the star, while the second, much less luminous, is around 30 astronomical units away. According to scientists, the inner ring has a temperature of minus 233 degrees Celsius, or 450 degrees Fahrenheit, and a mass of 0.01 Earth masses. What's more, this ring proved to be a formidable marker for providing a potential indication of the detected exoplanet's inclination. Indeed, when this observation was made, only the exoplanet Proxima Centauri b had been detected. This prompted astronomers to take an even closer look at Proxima's surroundings, which were clearly home to more than just a single planet. In comparison, this belt would have properties equivalent to those of our Kuiper belt. According to these latest observations, Proxima is most likely surrounded by a complex planetary system, bearing a striking resemblance to our own solar system. This suggests that Proxima and its planet followed a similar process. The hypothesis that Proxima b has been captured no longer holds water. This exoplanet was indeed formed in this atypical system. Moreover, the discovery of 2 other planets in the following years has since supported this idea. However, the existence of these rings was soon called into question. The following year, a study echoing the findings of the Spanish team examined the 10 hours of observations already made on March 24, 2017. But this new study, unlike the first, was not based on the average brightness of the star during its observation period. And this second approach has radically changed the previous conclusion. It turns out that in reality, Proxima's luminosity increased by a factor of 1,000 in less than 10 seconds, before returning to its initial appearance in just under a minute. In other words, Proxima suffered an extremely powerful, particularly brief and confusing event. The reflection of red light on particles, simulating rings, was nothing more than an excess of luminosity due to a stellar eruption. Nevertheless, the phenomenon is not at all exceptional and is reminiscent of the well-known behavior of red dwarfs, renowned for their somewhat explosive temperament. Proxima Centauri is no exception to the rule, which for those looking for habitable planets precisely in this zone does not bode well. Let's get closer to these unexplored worlds and take a closer look. Let's start by getting to know Proxima c, better known as Gliese 551c. This is the most distant of the 3 planets detected near the Proxima star. Its detection was announced in April 2019 by an Italian team of astrophysicists led by Mario Damaso. It was while studying the radial velocity data of the Proxima star using the HARPS high-precision spectrograph at the Chile-based European Southern Observatory that they noticed movements. Although insignificant, these can only be explained by the presence of a significant object, namely a planet. But to confirm the existence of such an object, further studies were required. Scientists took a closer look at recovery images from the Hubble telescope, which dated back to 1995. But instead of focusing, as in the 1990s, on potential planets with orbital periods of no more than 1,000 Earth days, they widened their search perimeter. After reanalyzing a wealth of astronomical data collected by Hubble, the researchers confirmed that there were indeed signs of an exoplanet in the vicinity of Proxima. As a result, the existence of Proxima c was confirmed in 2020, as it has a long orbital period. Images of Proxima c were even unveiled to the general public, thanks to the Sphere instrument on the European Southern Observatory's Very Large Telescope. Proxima c is therefore the first exoplanet, and the closest to our Earth, to have been immortalized by a lens. Together, these 3 studies have provided a wealth of information about this exoplanet. We now know that its mass is 7 times that of Earth, placing it in the category of super-Earths and mini-Neptunes. It takes more than 5 years to complete a full orbit, lasting exactly 1,928 days. This duration is of course related to its distance from the star Proxima, of which it is about 1.5 astronomical units away, i.e., almost 220 million kilometers, or 135 million miles. Given this configuration, could Proxima c harbor any form of life? This is highly unlikely, as life evolves well beyond the snow line, with the star's habitability zone lying between 0.05 and 0.1 astronomical units. With its equilibrium temperature estimated at just 39 kelvins, or around -234 degrees Celsius, it's likely that water can only exist there in its frozen form. Indeed, if Proxima c isn't a Lilliputian version of the famous gas giant Neptune, and indeed turns out to be a super-Earth, it may be covered by a thick mantle of ice. Let's continue our journey towards the star Proxima. The second planet we come across is Proxima b, also known as Gliese 551b. As mentioned earlier, this is the very first exoplanet discovered orbiting the star Proxima. As you can see, in terms of size, it's much larger, probably twice the size of its neighbor. Closer to its host star, at just over 7 million kilometers or 4 million miles, it orbits in 11.2 Earth days, receiving around 79% of the heat our Earth receives from the Sun. If it weren't for its sandy hues, it could almost be mistaken for our beautiful blue planet, couldn't it? Indeed, Proxima b is quite similar to our Earth in terms of mass, estimated to be at least 1.27 times that of Earth. Likewise, its radius appears slightly larger. But above all, because of its position, this exoplanet evolves in the habitable zone of the red dwarf, which grants it mild temperatures, particularly suited to the presence of liquid water on its surface. While the distance separating it from its host star gives it a temperate climate, let's not forget that the latter is a red dwarf, a star much colder than our Sun and up to 1,000 times less luminous. Proxima b is therefore much closer to its life vector than we are to the Sun, the distance being less than that separating the latter from Mercury. And this is not without consequences. Proxima b is strongly subject to the tidal forces of its parent star, which unfortunately synchronizes its period of rotation around its own axis with that of its orbit around the star. In other words, this exoplanet is tidally locked, probably exposing the same face to its host star at all times. But once again, this is only a hypothesis. Indeed, depending on the resonance with which it interacts with its local sun, the consequences might not be so catastrophic. In the case of a 1-to-1 resonance, the most pessimistic hypothesis, one of its faces would be eternally exposed to the star, with temperatures never falling below 40 degrees Celsius or 104 degrees Fahrenheit. The other side, meanwhile, would be plunged into endless icy darkness. On the other hand, if it were a 3-to-2 resonance, Proxima b could prove much more hospitable, although conditions would be far from those we enjoy on Earth. This means that the planet would be able to make 3 rotations on its own axis over a period of 2 years. Taking into account its orbit, which lasts 11.2 Earth days, this means that a day on Proxima b would stretch over 7.5 of our days, with relatively significant temperature variations. While this hypothesis remains conceivable, the presence of an atmosphere and a hydrosphere, both indispensable to the existence of any form of life, may generate other problems. Sometimes cold, sometimes hot, these elements generate irregular heating and thus convective movements, manifested by winds and ocean currents. Various models suggest that if Proxima b is covered by a gigantic ocean, the heat from the sunlit hemisphere could spread widely over the cold hemisphere along the equator. Different simulations based on more or less massive atmospheres put forward other ideas. In the case of a relatively thin atmosphere, heat distribution could be very uneven across the planet's surface. Conversely, a much more massive atmosphere, allowing maximum concentration of water vapor, could lead to more even heating, which would have an unexpected consequence. Proxima b would be largely ice-free, offering much more hospitable temperatures for the development of life. Now let's discover the third planet in this system. This is Proxima d, also called Gliese 551d by scientists. It lies just 4 million kilometers or 2.5 million miles from its host star, and is therefore located in the hot zone, slightly below the limit of the habitable region. What makes it special? It is one of the lightest exoplanets ever detected using the radial velocity technique, with an estimated mass a quarter that of our Earth. Its discovery, albeit recent, has proved to be a technical feat. With such a tiny mass, the gravitational effect it produces on its host star is extremely weak. As a reminder, the radial velocity technique involves measuring the tiny movements of a star caused by the gravitational attraction of an orbiting planet. In this case, it enables us to observe with incredible precision oscillations of Proxima Centauri measured back and forth at just 1.4 kilometers per hour or 1 mile per hour. It's easy to see why this type of object is so difficult to detect. Lasting 5 days, these small variations indicated the time needed for the planet to make a complete orbit around its star. It took the scientists almost 100 nights of observation to reach this conclusion, as the signal emitted by the star was particularly weak. But their patience was rewarded, as this discovery paved the way for many others. Because of its location in the system, Proxima d is probably a rocky planet. Its singularly low mass certainly prevents it from trapping gas in the same way as gas giants such as Jupiter, Saturn, or Neptune. It undeniably resembles a devastated Earth. Scorched in places by a constant average surface temperature reaching 87 degrees Celsius or 189 degrees Fahrenheit, while the polar regions experience more moderate circumstances. If this planet isn't the most hospitable, its discovery is nonetheless of the utmost importance. It suggests that all stars have their own multiplanetary systems. Thanks to the espresso spectrograph, it's a safe bet that many other planets previously invisible to the instruments will finally be unearthed. Another high-precision instrument will soon be pointed in the direction of Proxima c. Called Ristretto, it should enable us to observe Proxima's light reflected by the exoplanet. When this new instrument is in action, it will enable scientists to deepen their observations, and why not detect the hypothetical atmosphere or the possible presence of water? If the existence of these elements were to be confirmed on one of these planets, and on Proxima b in particular, it would be fantastic news. Proxima, as the closest star to us, is therefore an ideal target for scientists hoping one day to find any trace of life beyond our solar system. This is especially true now that Proxima b has been detected and located within the habitable zone of this red dwarf. However, there is much debate among scientists about the prospects of life near this category of stars, namely cool, low-mass M-type stars. These are among the most widespread in our galaxy, with a high frequency of exoplanets roughly comparable to Earth, and with equilibrium temperatures suitable for the presence of liquid water on their surfaces. However, red dwarfs are renowned for their unpredictable behavior, which has a particularly strong impact on their immediate environment. Indeed, these stars, although small, are active and unstable, with the usual stellar eruptions. As you may have guessed, Proxima is no exception to this rule. As part of a study of Proxima, covering some 40 hours of observation between April and July 2019, a team of researchers from the University of Colorado recorded a most spectacular stellar flare. It was recorded on the 1st of May, 2019, by 5 of the 9 instruments pointed in its direction, including the Hubble Space Telescope, the TESS satellite, and the high-performance ALMA terrestrial radio telescope, which alone brought together more than 60 dishes. According to the study, the star became 14,000 times brighter in ultraviolet wavelengths in the space of a few seconds. Scientists were amazed by the exceptional power of this burst of radiation. To give you an idea of the scale of the phenomenon observed, it turned out to be almost 100 times more powerful than the strongest flares ever seen on our sun's surface. Although it didn't produce much visible light, this explosion was unusually intense in terms of ultraviolet and radio radiation. Lasting just 7 seconds, it therefore produced millimeter wave signals. For scientists, this was a momentous observation. It confirmed that stars are capable of blazing in the millimeter range. This new type of signal is a godsend for researchers trying to learn more about how stars produce their flares. All the more so, as during the hours Proxima was under observation, astrophysicists noted a multitude of other flares on the star's surface. Not only does this mean that this type of flare cannot be described as rare, but more importantly, that such events are probably a daily occurrence. In fact, another team of astronomers had already announced in 2017 that they had captured a stellar eruption on Proxima's surface. Phenomenally powerful, it is likely to have been capable of destroying any Earth-like life present in a certain area. For the planets orbiting Proxima, this finding is far from optimistic about the presence of any form of life, at least as we know it. For if there were life on Proxima Centauri's nearest planet, Proxima b, it would have to be very different from anything on Earth. If not, any living organism that has experienced this stellar eruption has inevitably had a rough time of it. Planets in the vicinity of this star, which experience this kind of cataclysm on an almost daily basis, may see their potential atmosphere dwindle over time, if they even have one at all. Stripped of this protective bubble, these exoplanets would no longer be capable of harboring any kind of life at all, as they would be fatally exposed to deadly solar storms. But once again, this is nothing more than speculation. The high-energy radiation produced by this red dwarf has yet to concretely reveal its impact on the immediate environment. Further observations will be needed to shed light on an exciting subject: planetary habitability alongside the Proxima star. Apart from the problems caused by these stellar eruptions, there's another parameter, and not the least important one, to consider for researchers of potentially habitable planets. This is the star's lifespan. Assuming our humanity lasts several million or billion years, it would be a shame to have chosen as our promised land a planet evolving around the corpse of a star, wouldn't it? By the time our Sun, in 1 billion years' time, begins its long transformation into a red giant, then undergoes a collapse followed by slow cooling, what will become of Proxima Centauri? A red dwarf is not to be confused with a low-mass star at the end of its life, having once shone brightly before slowly fading away. The latter has not undergone the same evolutionary process. A yellow dwarf at the end of its life generates helium fusion, gradually transforming into a red giant. Then, when this fuel is exhausted, it becomes an insignificant white dwarf, losing more and more of its luminosity until it glows red, before dying out forever and turning into a hypothetical black dwarf. While yellow dwarfs like our Sun have an estimated lifespan of 10 billion years, Proxima has a different destiny. Initially too small and hot to become luminous like yellow dwarfs, this star consumes its hydrogen extremely slowly. It belongs to the type of star with a convective interior. This means that energy flows from the core to the outer layers through the motions of the glowing plasma. Yellow stars, on the other hand, have a radiative interior, conducting their energy outwards from the core using a form of electromagnetic waves, thus rapidly stripping it of its fuel. Proxima, like all red dwarfs, has a particularly long lifespan, estimated at between a few tens and 1,000 billion years, or even more. By the time this red dwarf has exhausted all its resources and become a white dwarf in its turn, without passing through the red giant stage, it should gain considerably in luminosity. But before it reaches this stage, heating up its planetary system, a few billion years will have passed. Now you understand why this modest star is the focus of so much scientific attention. If other planets were to be discovered in its habitable zone, which is not excluded, the chances of conquering a new world would be greatly multiplied. As astrophysicists search for potential habitable extrasolar planets, they are equally on the lookout for hypothetical traces of extraterrestrial life. The SETI program for the search for extraterrestrial intelligence, created in the 1960s, is proof of this. On August 15, 1977, this collaborative program caused quite a stir. Jerry Emin, an astrophysicist from the state of Ohio, recorded a particularly strong signal with the Big Ear radio telescope, seemingly coming from a group of stars in the Sagittarius constellation. The signal astonished him so much that after printing the trace of this radio frequency, he circled it with a red line, then froze his amazement in the margin with an annotation, "Wow." This mysterious 72-second signal, emitted on the 1.42 GHz frequency, then became the famous signal "Wow." This strange message from the cosmos received by the Earth. However, listening to this radio wave was no accident. Indeed, before scientists set out to listen to the sky in the hope of detecting potential ET signals, they calibrated their equipment. To give themselves every chance of one day listening for such a signal, their radio telescope was set to a precise wavelength, known as the 21-centimeter ray. This choice was based on an obvious deduction. The electromagnetic radiation produced at this wavelength corresponds to that which best penetrates hydrogen. Hydrogen is the most abundant element in the cosmos. The recording of this signal came as a great and unexpected surprise, generating doubt. A more down-to-earth explanation was sought. Due to an international agreement, the frequency used is reserved exclusively for this program, precisely to avoid any terrestrial interference. What's more, no known natural phenomenon can emit such a signal. The hypothesis that a pulsar is at the origin of this signal has also been studied, with no concordant results. Even the possibility of a computer error in the system was considered, but dismissed for lack of evidence or recurrence. Finally, the passage of two comets through the radio telescope's listening field has been the subject of debate ever since, their existence having only been proven much later, in 2006 and 2008. For many scientists, however, the latter explanation does not seem credible at all, as various pieces of evidence support it. Since then, a complementary project, Breakthrough Listen, was launched in 2015. Its aim is to focus on unexplored radio frequencies identical to those commonly used on Earth for all kinds of communications. In April and May 2019, radio signals were intercepted from the vicinity of the Proxima Centauri star. The source of these signals has been named BLC-1 for Breakthrough Listen Candidate 1. While astronomers on this project regularly spot unusual radio wave bursts, these are usually explained by human interference. But this latest one, detected 5 times during some 30 hours of observation, has passed various tests, greatly arousing their curiosity. All the more so as it occupies a particularly narrow band of the radio spectrum, the only source known to date capable of transmitting at 982 MHz being human. For scientists, the task now is to sort things out. Is it really an extraterrestrial technosignature, as many exobiologists and science fiction novelists dream? Or is it yet another case of interference from Earth? But researchers aren't content to just listen to the universe. Over the past few decades, several messages have been sent to specific regions of space, addressed to a potential extraterrestrial civilization. While most messages have been transmitted by radio, some in the form of images encrypted in binary code, others have been composed of drawings, like the one attached to the Pioneer 10 probe. An even more sophisticated message, 2 golden disks containing images of the Earth, musical data or ambient sounds of our planet traveled through space on the Voyager 1 and 2 probes. These messages, like bottles thrown into the sea, should they one day encounter a form of life, are nevertheless no guarantee of a future dialogue between civilizations. Who is to say that a potential life form beyond our planet would be able to intercept these messages? After all, these supposed extraterrestrials may not perceive their environment as we do. Their language could have evolved in a telepathic mode, rendering sight and hearing obsolete. Nevertheless, as long as the contrary has not been formally demonstrated, the hope of finding a trace of life in the Alpha Proxima system, or at the very least a habitable planet, why not one that can be terraformed, is still alive and well. For the record, let's not forget that our own system could yet reveal some of its secrets. Astrophysicists suggest that a 9th planet, as yet unobserved, may exist in the outer reaches of our solar system, somewhere in the Kuiper Belt. If the existence of this celestial body were to be confirmed, which could well happen in the very near future, it could explain the unusual motions observed with certain objects evolving beyond Pluto's orbit. So, With our eyes riveted on the promising Alpha Centauri system in search of exoplanets, even if it is a fantasy, the idea is not absurd. Especially as techniques for detecting distant objects, even those of low mass, are becoming increasingly precise. But while we await major revelations, such as why not the discovery of an exoplanet similar in every way to our Earth, let's take a look at what life might look like on the planets we've observed. As we've seen, Proxima d is far too close to its host star to offer us a comfortable place in the Sun. Its telluric appearance hides an inferno of fire and ice, as the planet is trapped in a synchronous rotation. On the one hand, its sky is eternally ablaze with the glow of the red dwarf it borders, its atmosphere a toxic mixture of gases. Violent, fiery winds plow its rocky surface, resembling a desert of molten glass. Its night side, also desolate, is an ice abyss, plunged forever into cosmic darkness. Even if any trace of life could ever have formed on this planet, even if only in the form of bacteria, at present it can only be completely annihilated, at least on its day side. As for Proxima c, the most distant of the three planets orbiting Proxima, the picture is not much brighter. Its status is still unclear. Is it a gas giant resembling a mini Neptune, or a super-Earth? In either case, it's an extremely cold world, far too far from the habitable zone of its host star. However, if it turns out to be a super-Earth, the idea that it could harbor life in a form other than the one we know may not be so far-fetched. Imagine that this planet contains large quantities of water. In that case, it could be entirely covered by oceans that are completely frozen, or at least several kilometers or miles deep. Unwelcoming, isn't it? Now imagine what its seabed might look like. Although completely deprived of the weak glow emitted by the local sun, they could nevertheless experience temperatures more favorable to the development of a certain biosphere. The regular activity of submarine volcanoes could enable this singular environment to keep simple multicellular organisms alive in such ocean depths. Of course, this is all speculation, not to say daydreaming. Let's now turn our attention to the most attractive of these three planets, Proxima b, which has enthusiasts enthralled. While it does indeed lie in the temperate zone surrounding the red dwarf, its proximity makes it particularly vulnerable. As it too is locked in by tidal forces, this planet probably consists of two distinct worlds, a day side and a night side. In theory, its overall temperature allows for the presence of liquid water on its surface, the supreme condition for all life. But does it still have an atmosphere, which is also essential? If so, it would be plausible for temperatures to be in the region of -30 degrees Celsius or -22 degrees Fahrenheit on the shady side, and 30 degrees Celsius or 86 degrees Fahrenheit on the light side. Unfortunately, if an atmosphere is or was present on the surface of Proxima b, some scientists agree that its existence is highly compromised. Remember the activity described earlier of Proxima Centauri, its recurring tantrums concretized by intense ionizing rays and repeated solar storms. Because of its short distance from its red dwarf, this planet is particularly exposed to its X-rays and ultraviolet rays. According to researchers, the latter could be up to 100 times more powerful than those we receive from the Sun. Despite this, the idea that Proxima b still has an atmosphere has not been completely ruled out. Numerous simulations of planetary worlds evolving in systems similar to Proxima Centauri show that the majority of planets are either completely covered by a vast, thick, icy ocean or have become barren rocks. Far rarer planetary objects comparable to our Earth, however, exist in orbit around old red dwarfs that have become less active. In the case of Proxima b, this relatively massive super-Earth appears to have absorbed large quantities of water particles and surrounding gas in its early stages. If this hypothesis is confirmed, a particularly dense atmosphere of oxygen and nitrogen could envelop it, masking a mysterious oceanic world. The existence of this atmosphere, potentially 10 times more abundant than that which protects our Earth and of oceans several kilometers deep, cannot be ruled out. Despite the explosive nature of its neighboring star, Proxima b has not yet been completely stripped. Some scientists even consider that it may have retained a sufficient atmosphere and a sizable hydrosphere. The planet's large size is therefore a definitive advantage, especially since the presence of a magnetic field is highly probable. A planet of this size, though tidally locked to its star, may not yet have come to a complete stop in its rotation. Its core could still be hot and mobile for a long time, generating a substantial magnetic field, perhaps even greater than that of our Earth. Now imagine that these three factors were combined: a dense atmosphere, a considerable hydrosphere, and a strong magnetic field. They would provide the conditions necessary for the survival of many forms of life, protecting them to a large extent from the harmful and devastating radiation of the Proxima star. Although this world, if it really exists, is plausibly an essentially aquatic one, failing to be truly hospitable, it remains no less captivating. In a recent study of 17 exoplanets, NASA's Dr. Lene Quick and her colleagues shed some light on their habitability. According to their findings, Proxima b, like the other extraterrestrial worlds studied, may unfortunately not be as hospitable as hoped. On the one hand, it seems less dense than our Earth, suggesting that it would be composed essentially of ice and water rather than rock. The surface temperature, a priori colder than first estimated, implies that this oceanic planet would be completely covered by a mantle of ice. The thickness of this mantle is estimated at nearly 58 meters or 190 feet. On the other hand, based on the intensity of geysers on Europa, one of Jupiter's moons, they calculated that Proxima b could have an extremely high rate of geyser activity. This appears to be hundreds or even thousands of times greater. Cryovolcanic eruptions in the deep ocean would expel considerable plumes of steam and ice particles far from the surface. Proxima b would in fact be dotted with abundant geysers cutting through its ice mantle, especially as the latter appears to be much thinner than on many similar objects. All these assumptions are based on observations made using the latest technology and on scientists' current knowledge. In the near future, as science continues to advance, these assumptions may be called into question. As you may have noticed, what seems to be true one day may turn out to be false the next. So who knows? Perhaps a future study will bring other conclusions, perhaps more favorable to a long-awaited discovery. With this in mind, scientists have long been considering sending out scouts in the form of onboard technologies. But what are their practicalities? Assuming that our current technology would allow such an expedition, how long would it take a spacecraft today to reach Proxima, the star that is our solar system's closest neighbor? Unfortunately, far too long. Currently, the fastest space probe ever designed is NASA's Parker Solar Probe. Launched in August 2018 to study the outer atmospheric layers of our Sun, it has been setting record after record ever since. Its latest came on September 27, 2023, when it reached a record speed of 635,000 kilometers per hour, or 395,000 miles per hour. This is 15 times faster than the fastest manned spacecraft. If we could travel at the same speed, it would still take us almost 7,300 years to reach Proxima Centauri. Assuming we could travel at the speed of light, this journey would be reduced to 4.2 years. To date, only 2 probes have crossed the boundary of our solar system. Launched on September 5, 1977, the Voyager 1 and 2 probes are the first man-made objects to travel through interstellar space. Voyager 1 was the first to cross this boundary in 2012, 35 years after its launch. It has enabled scientists to learn more about our Sun, its interactions with particles and magnetic fields outside our heliosphere. These observations have provided key information for future missions. As for the Pioneer 10 and 11 probes and the New Horizons probe, launched respectively in 1972 and 2006, while they have reached the limits of our solar system, the former are no longer in a position to emit anything. New Horizons, whose primary mission was to fly over the planetary objects of our solar system, will never be able to catch up with the Voyager probes. As you can see, space travel to the Proxima star is still a fiction. NASA's ambition was to develop a technology that would enable a probe to travel at a considerable speed, around 10% of the speed of light, in order to complete the long journey in just 44 years. At least that's what the team at NASA's Jet Propulsion Laboratory was aiming for in 2016, with the goal of sending a probe to explore Proxima b by 2069. To give you a benchmark, it would take Voyager 1 around 80,000 years, assuming it ran into no obstacles, to get close to Proxima Centauri, its cruising speed being 16 kilometers per second or 10 miles per second. NASA is therefore looking into ways of reaching Proxima in the shortest possible time, especially since if this feat were to be achieved, it would still be more than 4 years before any recorded data would reach us on Earth. A major technological breakthrough is therefore essential if a mission of this scale is to succeed. A combustion engine powered by a nuclear fission reaction could achieve this. Unfortunately, according to scientific estimates, it would take 1,000 years. Engineering using pulsed nuclear propulsion, still theoretical, would enable this crossing to be made in a century, but without guaranteeing the safest possible journey, as its nuclear payload represents a considerable risk. According to astrophysicist Michael Gillon, nuclear fusion, provided that a nuclear fusion engine is mastered, which is still a long way off, would shorten the journey time to just 36 years. Faced with this more than ambitious project, NASA has finally associated its Innovative Advanced Concepts Program, or NIAC, with a private initiative called Breakthrough Starshot. Launched in 2016, Breakthrough Starshot is a commercial research and engineering project estimated to cost $100 million. Many visionaries who also dream of conquering space have taken part in this project, which aims to explore deep space and potentially discover other habitable planets. Their primary objective is to encourage technological innovation by bringing together eminent scientists to make a voyage to Proxima Centauri possible in a few decades' time. Research teams are hard at work on advanced technologies that will ultimately benefit humanity. These should revolutionize our understanding of the universe and offer future generations the opportunity to finally explore other interstellar worlds aboard spaceships. One of the main challenges facing researchers is to develop a propulsion system capable of propelling a spacecraft at a speed equivalent to 20% of the speed of light. To achieve this ambitious goal, researchers are currently developing 3 key programs. The first is the design of a miniaturized spacecraft known as starships. These nanoprobes, equipped with computer chips and a whole range of communication systems, must withstand the extreme conditions they will be confronted with. The second is the development of a propulsion system based on lightweight sails, the light sail system. Based on optical technology, these sails are made of a material only a few hundred atoms thick. Last but not least, the development of a ground infrastructure to supply, via a laser system, the energy required by this light sail to propel and steer the starships towards its destination, Alpha Centauri, and more specifically, the star Proxima and its planetary system. To multiply the chances of succeeding in this crazy gamble, 1,000 Starship ships, each weighing no more than a gram. Thanks to the laser's unrivaled power of 100 gigawatts, these nanovessels would then be able to reach a speed of around 20% of that of light. Like a swarm, these extraordinarily autonomous probes will progress with perfect synchronization to form a mesh network covering an area of around 100,000 kilometers or 62,000 miles in diameter. This process should ensure that a minimum number of probes, despite a high loss rate or poorly controlled direction, reach the coveted target of Proxima. The scientists' efforts have just been rewarded, with NASA selecting their concept for Phase 1 development under their NIAC, or Innovative Advanced Concepts program, at the start of 2024. The only solution at present, therefore, is to reverse the rocket. Instead of the rocket expelling a material to be used as fuel, it is necessary to launch something onto the vessel that will enable it to move forward. In this case, like the wind blowing over the sail of a boat, photons would strike the photovoil of each of these nanoprobes. Although scientists have made tremendous strides, such a mission is unlikely to see the light of day before 2075. The concept, though very promising, must overcome enormous difficulties. These include the robustness of the sail. Will it be able to withstand the heat generated by the laser beam? Or to sudden accelerations? Or the gas and dust it might encounter? On the other hand, control from Earth will be impossible. Scientists therefore have to develop genuine robotic probes. The swarm, as they are called, must be perfectly autonomous. Finally, the manufacture of this high-tech swarm and the construction of a terrestrial laser system, not to mention the research work, represent a staggering budgetary outlay. Even if each of these probes on a gram scale does not generate exorbitant manufacturing costs, the project as a whole is the most ambitious ever envisaged. In the silent immensity of space, the Alpha Centauri system shines like a distant promise, and like a lighthouse attracts our boldest dreams. Imagine a world where the stars are no longer out of reach, where the secrets of the universe are revealed to us on fabulous interstellar journeys. Proxima b, the exoplanet that's raising our wildest hopes, could hold the key to our deepest questions. Is it the cradle of extraterrestrial life? Do its oceans conceal strange forms of life? Is it a potential future home for mankind, or on the contrary, a place of nameless desolation, begging to be fled? The technological advances under development, these robotic probes that could one day split the vacuum of space, are not mere tools. They are messengers of our curiosity, probably the pioneers of a new era. Each of their discoveries, beyond helping us to take another step towards understanding our place in this great whole, will be a formidable legacy for our future generations. More than a scientific feat, the project to spin off Proxima using these solar minnesons is a veritable symbol. Alpha Centauri, and the Proxima system in particular, may still seem a long way off today, but every step we take brings us closer to the moment when we can say that we are travelers among the stars. And who knows, perhaps in just over a century's time, the first images of Proxima b will reach us.